In this lesson, we're going to look more at the structure of amino acids with regards to the charges, specifically how we describe them as a zwitterion at their isoelectric point. And then we're also going to look at the charge on amino acids when we are not at the isoelectric point. The first word we need to learn is zwitterion. So we know that ion means there's a charge, and Zwitter actually means the German for hybrid. So when we have an amino acid that has both a positive and a negative charge, it is a hybrid type of ion. It's neither a cation nor an anion because it's both. So we refer to that as a zwitterion. And we have to have both the positive and negative charge on their respective ends in order to have a zwitterion. Now, amino acids don't always exist as a zwitterion. When they exist as a zwitterion is when they are at the isoelectric point. This is also known as the pI value. And so this occurs when the pH of the solution equals the pI value, or the isoelectric point of the amino acid. Because iso means same, so we have some sameness in the electric. There's a positive and negative, but the magnitude is the same. And the pI values are a reference value. You'll be given those values in a reference table and use those. You don't have to memorize those either. So let's zoom in on this reference table. So this reference table at the top is what you'll actually get provided to you on the exam. I've zoomed in on a small section of that so that we can look at some of the information that's given there. First, we see the name and the abbreviation of each amino acid. We see the side chain, and this represents where it connects to the backbone of the amino acid. And then we have the pI values over here on the right. So every amino acid has its own pI value, and that pI value represents the pH at which the zwitterion is present. If we're not at that pH, then it doesn't exist as a zwitterion, and we'll talk in just a second about how we know how it exists. Let's look at alanine as an example. Alanine has a CH3 group, and that's all there is. This is where the bond is to the backbone, so there are no other carbon or hydrogen atoms there. The pI value is 6.11, which means when the solution has a pH of 6.11, alanine will exist as the zwitterion with both the positive and negative charge. Which amino acid has the lowest pI value? Hopefully, you see that it is threonine, which has a value of 5.60. Every amino acid has its own pI value. We've talked about how the amino acid exists with both a positive and negative charge as a zwitterion when pH is equal to pI. But we also need to look at how it exists when pH is less than pI and when pH is greater than pI. So when pH equals to pI, we have the zwitterion. It's overall neutral because we have a plus charge on one end and a minus on the other end. When we look at pH less than pI, and it doesn't matter what the pH is or what the pI is, we're just looking at a qualitative comparison. Anytime pH is less than pI, this is what the molecule will look like, and we will see the same pattern for every single amino acid. Notice this shows the generic R. That means it applies to all 20 amino acids. So when pH is less than pI, we're dealing with a solution that is more acidic than the pI value, and as a result, there is excess H plus in solution, because when pH is low, we have a lot of H plus. Now, when I look at my zwitterion and I think about the H plus, it's not going to be attracted to the NH3 plus because that's two positive charges. It will be attracted to the O minus, and it actually add on to that and will form the OH group. So we have a C double bond O, OH. As a result, we're left with just the NH3 plus charge. So we have an overall +1 charge because we basically neutralize the negative charge on the carboxylate ion. Now, let's look at what happens when pH is greater than pI. So when pH is greater than pI, we're dealing with a solution that is more basic than the pI value. That means we have excess OH minus. And when I look at that minus sign, it's not going to be attracted to the carboxylate group because that's a negative charge. It will be attracted to the NH3 plus from the zwitterion form, and it will actually steal away one of those hydrogens. And when it does, it's going to take the H plus, it's going to form water and leave us with NH2, which is neutral, and we're going to be left overall with a -1 charge. So this pattern will hold for every amino acid. You just have to compare the pH value that the solution is given, the solution that's given for you, and to the pI value of that particular amino acid. At what pH will leucine have a net charge of 0? Well, we know the pI is 6.04 because that's given. And if we want to have a net charge of 0, that means we need to have both the positive and negative, which means we need to have a zwitterion. And so the net charge of 0 will exist when pH equals 6.04, so that pH equals pI. What is the charge on threonine when pH equals 4.0? When we look at this problem, we see that our pH is less than pI. That means we're dealing with the more acidic environment, so more H plus, and it's going to be attracted to the OH minus, leaving us just with the NH3 plus charge, and so we will have a charge of +1. What is the charge on threonine when pH equals 7.0? The temptation is to say that it's going to be 0 because we like to think about the pH of 7 being neutral. But we're not just looking at the pH value, we have to compare it to our pI value. So pH is greater than pI here. So we're dealing with a more basic solution. We have more hydroxide, and that's going to steal away that H plus from the NH3 plus. So that will be neutral, no charge on that end. And then the other end will retain its negative charge, and so we'll have a charge of -1.